just take a few minutes. It's rather unfortunate that Ricardo is stuck in the traffic jam. So anyway, without taking much of your time, just give you a very short, please, some housekeeping announcements. Things we have a session until 11 o'clock for the coffee, before the coffee break. But this first session is going to be on integrated management of coastal and marine areas and chaired by Professor Stephen Hawkins from University of Southampton. I regret, I beg pardon for, on behalf of Ricardo, who could not join us here. So without taking much of your time, please switch off your cell phones in a silent mode. And let's start with Professor Stephen Hawkins. You won't be here. Yeah, the first one is here, no? Yeah. The floor is yours. And
Morning, everybody. I'm Steve Hawkins from the University of Southampton. I was working off an older version of the schedule. I thought I was chairing tomorrow, not today, so I'm rather casual. But fortunately, our first speaker is maintaining a standard dress and is wearing a tie. So I'm glad that sartorial elegance is maintained. So I'd like to introduce our plenary speaker, Thierry Chopin, from the cold waters of the Bay of Fundy, all the way here, to tell us about aquaculture in the context of management of coastal marine seas. So, please. I will tell you after 25 minutes, okay?
Okay. Yes, good morning, everybody. I am very pleased to be in the Canary Islands, and I would like to thank Ricardo and Gersand because you can see you can see how our sites look at the present time. All this white stuff, it's snow. So we are very pleased to be here. And another reason why I am very pleased to be here, it's because my parents were there in 1972, and they visited Lanzarote, and there is a picture of my parents on the dromedaries, and next week, with my wife, who is here, Cathy, we hope to do another picture 44 years later, and we will see what it is. Anyway, let me get to the talk of today. The coastal zone is a very busy place. And 2 years ago, I was in Japan, not very far from Hiroshima, which would be around here. And here is a coast, very populated. And here also there is a very famous shrine. And I was wondering how all that can cohabit. We have a lot of urbanism, but we have also aquaculture. All these things here are aquacultures. And also we have tourism and religions, all that together with a lot of ferries going across the aquaculture sites, and all that live together. So there is some lessons to learn there. In New Brunswick, in the Bay of Fundy, on the eastern side of Canada, it's also a very busy place. We did an exercise on where could we have exposed nearshore aquaculture. The aquaculture at the present time is all these black dotted points, but it wants to extend. But is there place, is there room for aquaculture? Well, not so much, because it's a busy place. Then, of course, we move to the Canary Islands. On my understanding, it's also a very busy place, especially with a lot of tourism. And the question is, where will aquaculture fit in all that? So I think there is a need for marine spatial planning and management, which should also include aquaculture. That's a diagram. As a matter of fact, a few years ago, I was at a conference in Gdańsk in Poland. And here we had also an exercise of marine spatial planning. And you can see there is aquaculture here, the fish, the seaweeds, the shellfish, but with all kind of other activities, because also the Baltic Sea is a very busy place. So everywhere it's a busy place, everywhere everybody wants a piece of the cake, a piece of the map on how do we organize all that. So I would like to talk about what we have been doing since 2000. We have been working on some things that in 2004 became known as integrated multi-trophic aquaculture here. And so I would like to explain what is integrated multi-trophic aquaculture and also why it should be the type of aquaculture we should develop in areas, in coastal areas where we want to have some management. So what is integrated multi-trophic aquaculture? At the beginning, we thought it was three components: the fish that you feed, and then the shellfish and the seaweeds. So how does it work? You add feed to the system, you feed your fish, that create a nutrient zone. We have different types of particles, the small particulate organic matter that doesn't go very far. So that's why you put your shellfish quite close to the fish. And you have the dissolved inorganic nutrient, dissolved nitrogen, dissolved phosphorus. They move further away, and that's why we have the seaweeds a little more downstream. So initially, we started with these three components, but we recognize it's more complicated than that. You have also large particulate organic matter that go to the bottom quite rapidly, and also the shellfish produce feces and pseudofeces, and that go to the bottom. So we need also to address what is depositing at the bottom. For that, we develop the deposit extractive aquaculture with some invertebrates like sea urchin, sea cucumber, why not lobster, sea worms. And also there is a fifth component, we have been working on it for the last 2 years, that's the microbes, the microbial component. We don't know much about it, generally speaking, but it seems to be a very important, significant component, because with the invertebrate at the bottom, it's all these bioturbation, these mineralizations, and that send back some dissolved inorganic nutrients back to the seaweed. So here is a full picture of IMTA, integrated multi-trophic aquaculture. I know it's a mouthful, so people sometimes say, just say IMTA. And then people say it's even too complicated. So if you don't remember IMTA, you can sing it. You remember village people, YMCA. You can do exactly the same thing with IMTA, YMTA, and it works, and then you remember it. So that's what we do here. And you can see we even have karaoke IMTA night. We have some of our graduate students. It was a workshop in Chile doing IMTA on the beach. So that's what IMTA is all about. So the IMTA concept is extremely flexible. IMTA for me is like the central overarching theme on which many variations can be developed. So it's just like in music, not the music of Frédéric Chopin, but the music of Johann Sebastian Bach. You know, he was very famous for theme and variations. Well, that's exactly that. We have a theme, we have the general IMTA theme, and we build many variations. So you have ta 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 ta, and then you do ta 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 ta, and you continue on many variations on always the same concept. What is the IMTA concept? It can be applied to open water, land-based system. It can be applied to marine and freshwater environment, and it can be applied in temperate cold, like in Canada, or subtropical, tropical climate, like here, also in the Canary Islands. It's important to choose the appropriate organisms. The organism must be at different trophic level, and they should have complementary function in the ecosystem. That's to distinguish IMTA from polyculture. Polyculture, you can have 3 species of fish together. It's all going towards the same direction, production of nutrients. We need different species doing complementary functions. Some provide nutrients, some absorb nutrients. That's what is important. And also, if we want to convince the aquaculture industry to go towards IMTA, all the species that you choose must have economic value, or the industry will see no interest in it. It's also very important to understand the word integrated, integration. For us, it means in proximity according to the ecosystem functioning. It doesn't mean an absolute distance. We spent 8 years in Canada to fight regulations that say you are not allowed to grow one species closer to another by 125 meters. It was a magic numbers coming, we don't know from where, and we spent 8 years. That's a long time for us scientists. For politicians, apparently 8 years was quite fast. But for us, it was a long battle, 125 meters, and I say, why 125 meters? And they could not understand, they could not say why. So I say, well, why not 152.3 meters? And they say, why 152 meters? I said, just like your 125. You have no justification, so let's go with magic number. It doesn't make sense. So as a matter of fact, what is important is how everything is linked together. So it can be at the region of a site, it could be at the level of a bay, a region, it depends how the system works. So we have many variations. I will just show you two extremes. We have in the Western world aquaculture at a small scale, where as a matter of fact, the type of IMTA we have is what I call fish. We start with fish. Most of the Western world aquaculture is fish, to which we add invertebrates and we add seaweeds. Compared to the other extreme, if you want, of IMTA, that's what we have, for example, in China, in Changgu Bay. Changgu Bay, all that, and that is 10 nautical miles, okay? So that's a huge distance. All that is seaweeds. So we start with seaweeds, we add the invertebrate, and we have the fish. There is not too many fish cages. Most of the fish aquaculture is on land in Spain. In Spain, in China. Okay, so that's the two extreme and a lot of variation in between. So are they apple and oranges? I don't think so. We can learn from both. We should work together towards more integrative solution. There is good things to learn from what we do in the West. There is good things to learn from what is happening in China, but also China has its limits. There is also a problem when you reach such huge scale. Okay, that's also important to understand. So let's go back to New Brunswick. In New Brunswick, we have a typical aquaculture site, so salmon cages, with here the feeding barge, and they are fed like that, to which we add mussels cages, and we add seaweed raft. And the idea also is to produce these different components, and also use them with different food, salmon, mussels, and seaweed wraps. So that's what we are trying to do. The different components, the salmon component, I don't say much, it's typical salmon aquaculture. The seaweed component, that's the inorganic component. So here you can see some of our lines here, and then that's one line, roughly 3/4 of a ton. So we need to mechanize all that, because you can have some very enthusiastic graduate students. After 3 lines, they are completely dead. So we need to mechanize all that. We have also, for the small organic particles, we have the mussels and other shellfish. That's the first raft we put in the water. That's the raft we have at the present time, concentric circles, and then you have lines of mussels. So each unit is roughly 60 tons. You can see the mussels underwater. When you are in a shop, you always see them close, you want them close, but underwater, really, these things are just siphon in, siphon out, okay? And these are wonderful machines. Each mussel filters approximately 4 to 6 liters of seawater per hour. So tremendous pump. Then now we are working on the large organic particle component. So we have a lot of work to do with the different type of raft we want to have. And you can see sea urchin, scallops, and sea cucumbers. That's what we want to work at the present time on. So really what we need is a major rethinking of what is an aquaculture farm and how it functions. It doesn't work only within the buoys or the GPS coordinate on the map. That's what humans do. They put 4 buoys and they say that's the limit of the site. That's obviously not how it works. So we have to work using an integrated coastal area management or ICAM strategy according to the different elements we need to consider. The large particulate organic nutrients, you can manage them within the site because they fall pretty much just under the cages. The small particulate organic nutrients, very close to the cage and maybe a little, but we are talking of 10, 20 meters, okay, very close to the site. The dissolving organic nutrients, that's where we start to work at the bay management or the coastal area management. And then when you have a region, when you have a lot of aquaculture, that's the cumulative impact of these different sites that you have to consider at the area level. And then the same thing when you want to manage disease and parasites, it's also at the level of the coastal area management. So we have to rethink a farm never work in isolation between 4 buoys, okay? That's very important. So different nutrients mean different strategy, both in space and in time, because you can have accumulation of nutrient at a certain time, but they can be mineralized a little later. And that is not a problem. So it's always with the, when you talk with modelers, is how big is the box and how long will your box be working. So the infrastructure for co-cultivated species should be placed accordingly. So that's our big problem at the present time, is we have to think beyond the limit of a traditional fish site. And that opening a lot of problems with present regulations. So we need for regulatory change instead of regulatory hurdles, and we need regulations that should be enabling and flexible if we want to develop innovative aquaculture practices. I heard last night that you have problem in the Canary Island about getting site lease for more than 1 species. Well, guess what? In Canada too. Okay, we have these problems. We have been working, we are progressing. Now the problem is not so much having several species on one site, which after all, it's what happened in aquaculture. If you think that you are cultivating only salmon or only sea bass or sea bream, dream on. You are growing, you are providing substrate. As soon as you provide substrate, you are growing other things than just your fish. So the idea of monoculture doesn't really mean anything. The second thing is where we are trying to have to progress in Canada is, now that they have admitted that we can have several species, is how can we have amendment more than 1 species at a time? If I want to do shellfish, if I want to do seaweed, why do I have to amend my site each time? Or can I have a global change? That's still a lot of work. So also what is very interesting is through IMTA, there is a renewed interest on the mariculture of seaweed, and I will show you why. Because of the biomass you can produce, the ecosystem services, and also novel use. So seaweeds are excellent nutrient scrubbers, especially nitrogen, phosphorus, and carbon. So we should take advantage of these nutrients, because in moderation, which means within the assimilative capacity of the ecosystem, they are not waste. I am tired of hearing nitrogen is a waste, nitrogen is a pollutant. No, nitrogen, not in excess, is a good thing. So really, there is a good nutrient and the bad nutrient, just like there is a good cop and the bad cop in American movies. So that's the same thing. It's all about recycling. You know, when you are in a hotel, you get your 2 garbage cans, the normal one, the recycled one. It's okay. In your hotel, recycling is okay. In your office, in your garden, in your farm on land, recycling is okay. So why is recycling not okay at a farm in the aquatic environment? It doesn't make sense. So we should give a value to recapturing feed and energy, which otherwise will be lost, and then use it, convert it into other commercial crops. So we should give a value to these ecosystem services. We will have first to recognize what is the value of ecosystem services. We will have to give a value to it, and then use them as financial tool to be an incentive for the aquaculture industry to change its practices. So that leads us to the concept of nutrient trading credit. A lot of people get excited about carbon trading credit, carbon tax, carbon credit and everything. It's about time we think bigger than just carbon, and in the coastal environment, it should be nutrient trading credits. For example, the case of seaweed aquaculture, 23.8 million tons worth $6.4 billion US. If I look at the composition, the average composition of seaweeds, 0.35% of nitrogen, 0.04% of phosphorus, 3% of carbon, and the value of how much it takes to remove 1 kilo of these elements when you use, for example, waste treatment facilities that just outside of Toronto in Canada. That's the value, $10 to $30 per kilo of nitrogen, $4 per kilo of phosphorus, $30 per ton of carbon. And that is very important. Here we are talking tons, here we are talking kilos. Whoops. Yeah, so tons on kilos, so there is a factor 1,000. So as a matter of fact, there is more money to be made with nitrogen and phosphorus than with carbon, okay? And nobody is thinking about that. So if we estimate the ecosystem services of seaweeds, it's between 892 million and 2.5 billion US dollar, which as a matter of fact is equivalent to 40% of their present commercial value. And as a matter of fact, we never think in this term of putting a value on ecosystem services. Most of the time, the seaweeds and the shellfish and the fish are being valued only on their biomass and food trading value. We had to add that in business plan. We have to add the value of ecosystem services to give the true value of IMTA. Another aspect with seaweeds, seaweeds can be cultivated without fertilizer and agrochemicals. The fertilizing comes from the fish in an IMTA operation. Another thing that is maybe very simple to say, seaweed do not need irrigation, okay? So they are in the water, I don't need to irrigate them. At the present time, irrigation, access to water is a big problem on this planet, but not with seaweed cultivation. Seaweed cultivation doesn't need more arable soil and land transformation. We don't need deforestation. And seaweed also can be used for habitat restoration. They do a lot of that in Japan, for example. Seaweed also in aquaculture are the only components that provide oxygen, while the other one, animals and microbes, are consuming oxygen. Seaweeds can sequester carbon dioxide, so even if it is transient, they can do it. So as a matter of fact, we could put seaweed within the debate of global warming. Another thing that is also very important, seaweed also, by sequestering carbon dioxide, could have a role to play in ocean acidification. I should be very clear, when I say ocean acidification, I am talking about the impact of seaweed on acidification, but not on the global oceans. We will never grow enough seaweeds to change the pH of an Atlantic Ocean, the Pacific Ocean, or whatever. I am talking about an impact at the coastal level. At a small scale, I think we can have an impact, because the chemistry, and that's the only chemical formula I show you, CO2 plus water plus carbonate give you bicarbonate, and the problem is when the equilibrium goes that way, we get more and more bicarbonate, and that's not available to shellfish, that's not available to coral reef, to calcify, okay? So that's a big problem. But if you reduce that in good old chemistry, if I reduce that, I should be able to reverse some of my equilibrium to go back to the carbonate, and as a matter of fact, providing an environment for calcification. And as a matter of fact, as a matter of fact, that's exactly where we are. We published that just yesterday, a paper on ocean acidification and aquaculture, where we think IMTA can play a role, for example, in shellfish hatcheries. Just grow seaweeds before the water goes in the shellfish hatcheries, increase the pH, move it to the shellfish hatcheries, then you will not have local acidification problems. So we think that IMTA, by its strategy of diversification, fish, seaweed, and invertebrate, could be economic risk mitigation and management option to address pending climate change. You can have also seaweed in fish meals. We have been working on that for 2 years. We have also different products, biochar, methane, bioethanol, biofuel, biodieels. We could also combine seaweed cultivation with renewable energy park, where you combine wind farms and aquaculture. That can be an interesting concept. We could also talk about integrated sequential biorefinery. That's when you do more than one thing with one product. At the present time, it's too much one species, one process, one product. What we have to do is to move towards one species, several processes, several products. And that's what is integrated sequential biorefinery. You have the biomass, you have the ecosystem, you process it, you end up with integrated sequential biorefinery. It's a kind of black box, but you know that the black boxes are orange, so that's why I put it in this color. For seaweeds, you get different products. The bio-based high-value molecules, food, fed, agricultural, chemical, pharmaceutical, and those things. On the low values, that's the biofuel, the biodiesel, the biogas, and those things. So as a matter of fact, I am much more interested in working on that than on that. Here, it's a high-value compound. Here, to be competitive with the existing fossil biofuel, which is gas, I will have on that the value I got before the price of gas going down. It was to produce my seaweed at 40 cents a ton. I cannot do that, okay? I'm much interested in several dollars per kilos I can get here, okay? So that's what we do with our IMTA product. We use them for human consumption, in cosmetics, in fish meals, eco-certified salmon, with Loblaw, which is the biggest food retailer in Canada, organic certified kelps on biochar production. Here, since last year, our IMTA kelp are organically certified. And also last March, we created a beer with kelp. So here we are with the owner of the beer brewery. And here we are in the lab, you see beer in beakers, always a minimum of 3 replicates. So you could do statistic analysis. That's a very interesting beer. So we need to integrate the economic and social aspect of IMTA. What is the value of the biomitigative effect of IMTA? We did 2 studies. One that was published last year with a contagion behavior method. So we work with economists. We look at what is the value of increasing the salmon consumption, first with people that are already consuming salmon. That will increase the value between $280 to $1.5 billion per year. And we have a new publication that should come out next week or the week after. We do it this time with people that are not purchasing salmon at the present time. Will they increase their consumption? Yes, it's worth 43 to 65 million of dollars. Intangible social benefits, that's what we do also with social scientists. What's your perception of aquaculture in New York State, for example? A lot of people don't know where their fish, where their cow come from. Some positive, some negative. We show them a 12-minute video, IMTA videos. The indifferent have disappeared. You have 88% positive and still 12% negative, but a complete shift toward positive things. So the economic and societal implication of the adoption of IMTA practices are not negligible. It's time for the turquoise revolution. When you combine a greener and blue revolution, you get a turquoise revolution. It's time for the application of aquanomic principle in the management of aquatic field, the proper valuation of ecosystem services provided by extractive species, and the implementation of nutrient trading credits. Just very briefly, we have worked on the marine IMTA part. We can do the same with the freshwater part. It's a combination of fish and plant, but let's not forget in this thing, it's very important, the microbes and the worms. The same type of benefits we can have. And also what is very important is to take IMTA, what we call from the egg to the plate IMTA, freshwater plus marine, egg to the plate IMTA. So all that takes time to develop. So science and society need time to things and evolve. IMTA will not open overnight. It will take a lot of time, especially in the Western world. We are still in the infancy of Western IMTA. Some people are against fast food. I am against fast science. It will take time for things to happen. And on that, I thank you very much. Here is my website, and here is a video where we talk about seaweeds and IMTA. And that will be my ultimate integration pictures. Thank you very much.
So we have time for one or two quick questions.
Yeah, it's a tremendous presentation, and I suppose there's two aspects to it that I found very interesting. One thing is that, and it's a big issue for aquaculture right across the world, which is regulatory flexibility. And in parallel with that, there's public perceptions, and they're quite closely linked. And I think a particular positive feature of this approach, which was evident from the public preference study there, is public perceptions are very positive. And if you have public perception on your side, then you can address the regulatory issues. And I would like to emphasize that. So thank you.
Other questions come out? I'm a bit concerned about the autocorrelation of facts and prerequisites of being.
Yeah, that's right.
Temporal autocorrelation there, so there's problems.
The thing is, we always talk about IMTA is cleaning up the mess of fish farming. It appears that way, the way it's presented all over. There are situations all over the world, like for instance, if you take Indian aquaculture, it's basically called Indian major carp culture. It's integrated. They have 3 different species working at 3 different trophic levels. This is producing about 3 million tons. So this is where we've got to always think about. I can fully understand with the coastal management and things like that, what you're doing is unique. This is where we've got to strengthen what is done in New Brunswick is happening nowhere else. But we've got to remember that there are other situations which have been used forever. And this is some of the situations where you have tilapia and shrimp together. These are things which are being developed in different places. You should not forget that.
No, I think it's very important. I just show you one slide where I took the 2 extreme. What's happened in Canada, what happened in China. In half an hour, I didn't have time to, so I cut a lot of slides, but there is a lot of other type of integrated aquaculture. There is green water aquaculture. There is rice and fish aquaculture. All that are versions of IMTA. People have called them over the time many different things, but as a matter of fact, yes, IMTA, the way we do it is relatively new, but the concept itself is very old and with very sustainable system for centuries. And yes, in India, definitely there are some very good systems.
Okay, well, thanks again for a great plenary talk at great start for the conference. I'm sure there's various things we can come to in the discussion sections later.
Okay. Hi to everybody. Thanks a lot for being here. So, I am certainly sure I'm not going to speak for 30 minutes, but for sure more than 15, so let's see. Okay, for me, just to begin with, for me it's a real pleasure to be here. As some of you may know, I was actually born in Gran Canaria, here in this city. Actually, I was born in this building, just a couple of rooms in that direction. This was a military hospital when I was born, and I was born here. So I am almost, not just close to home, but I am almost at home. Okay, yeah. I am a little bit, say, strange in a marine biology, marine ecology meeting simply because I am actually a terrestrial ecologist and terrestrial biogeographist. But I am also a very good friend from the local people organizing the meeting, and they consider that I have something nice or something interesting to tell to you. This is what I am actually going to do. So my idea is just to try to open a little bit your minds to things that perhaps you have never think about, and that actually is what we are currently researching. Okay, that's the main idea. It's a pity. Gran Canaria used to be a really light city in winter, and this is the reason why you are going to not to be able to see too much because of the high irradiation, but I hope you will be at least able to follow my talk. Okay, this is a short outline I'm going to speak today. First, I will begin just a little bit with island biogeography beneath the seas. Islands are not just emerged entities. Then I'm going to speak a little bit about a very special case of seamounts called guyotts, where I think there is a special case of interaction among terrestrial and marine island biogeography that I think it's worth to explore. Then a little bit about biogeographical implications on guyotts, of the glacial cycles. And finally, I will try to work with a working example about the case of the Eastern Canary guyotts here in the archipelago. Okay. Let's begin with the first idea, island biogeography beneath the sea. Islands, although we really used to define them as a portion of land surrounded by sea or by water, there may be also islands beneath the sea level, as I would like to show you. Usually, when you open a book about island biogeography, you will find such sort of examples. There are different kinds of insularity, you see. Here, the normal island with the continent relations, or here this is what we call sky islands, or mountain tops that are separated by other mountain tops, but by flat valleys, even lakes that are separated by other lakes by land matrices, or finally what we called habitat island, in this case, a forest that is separated by some lonely trees by some matrix. This may have been in the past a continuous forest fragment. Today, it is separated usually because of human intervention. But of course, there are also islands beneath the sea level, and here is an example. Here we do have flat seamounts that we call actually guyotts, and you see they are both beneath the sea level, but we can find here an interrelation between such mountain tops also that is worth to study by island biogeography. Even if they are not properly geographic islands, they are biological islands. And the same happens with the abyssal trenches. For instance, here in this one, with this one, they may be related by fluxes, genetic fluxes, demographic fluxes, as used to happen in, say, normal islands or emerged islands. Actually, very recently, a good friend of mine, Mike Dawson, has published in Global Ecology and Biogeography a very nice work about insular entities. And in this table, he makes a relation of insular entities according to their marine, littoral, terrestrial characteristics, and if there happen or no evolutionary processes as well. And I have here include all of them, and they are those that relate with the marine environments. They have all a red line. You see, the first group is sea surrounded by land or seals, and there we have already island seas like Caspio Sea or Aral Sea, marine lakes like those in, for instance, Belau in the Pacific Ocean, pocket basins or trenches. We are going to see now a map of the trenches, deep ocean trenches around the world. Then we do have as well habitats surrounded by sea, like the barrier islands, cold seps or cold hydrothermal vents. Then the known continental islands, granitic ephemerals, also hydrothermal vents. They are, of course, islands as well. Island arcs, Lophelia Islands, mangrove, oceanic islands, including atolls, and so forth. And finally, even organic faults on the seafloor like whale faults or seamounts in green, because this is from which I'm going to speak now a little bit more. And you see that many of them have littoral characteristics, some of them terrestrial, and many of them also share evolutionary dynamics. The result is that there are some ecological and evolutionary processes that happen simultaneously both in marine and terrestrial islands. And among them, why not isolation, species-area relationships, impoverishment, disharmony, density compensation, island syndrome, evolutionary divergence, or even endemicity. Although we do know that endemicity used to drop in marine community related to terrestrial communities, mainly because of the sea is not that big barrier for seed dispersal or for genetic flux as the air happened to be. Okay, I just picked this from internet yesterday, and you see here we have the world distribution of the deep ocean trenches, and you see they behave like archipelagos. We can find them in the Atlantic Ocean, here in the Caribbean zone, or in the South Sandwich zone. Then we do have them also here in the Andean coast, South American coast, and for sure the big majority of them in the Pacific Ocean, the Aleutian Trench, the Kuril Trench, the Japanese Trench, the Mariana Trench, Philippines Trench, and so forth. So they behave as island arcs that are actually behind those trenches. And we do study island arcs, why not studying trenches as well? As I told you already, I'm going to speak a little bit more today just about seamounts. And we can define it as a geological elevation that reaches a minimum of 1 kilometer above the seafloor. Well, taking that definition into consideration, there may be some 0.1 million seamounts in the world ocean. 0.1 million seamounts, just to compare with. We are not sure how many islands there are. There are calculations that said that some 20,000 islands larger than 1 square kilometer. Other people speak about 500,000 islands. And oceanic islands, that means islands that have been able to form due to the accumulation of magma from the seafloor, there are no more than 2,000 in the whole world. 2,000, from then 11 in the Canaries. Okay? So, if we sum up abyssal hills and other accidents not reaching this 1 kilometer height, we can speak without problem about 1 million such features in the ocean floor. Of them, only 30,000 have been already identified. And from them, just 1,000 in the Atlantic Ocean. And at a global scale, only 350 have been studied, and just 100 with a certain detail, as the ones I'm going to speak today. Only a teeny portion of the seamounts are guyots, and here I have to explain that. But before, I would like to show you a map of the distribution of the seamounts around the world. Well, I hope you are able to see that there are a lot of them. No? Just with that idea, it's okay for me. It is really interesting some places where they seem not to be nothing, like here, but everywhere they are full of seamounts waiting to be studied. Okay, guyot's a special case of interaction among terrestrial and marine island biogeography. Guyot's first idea, where this strange name came from. There was a Swiss geologist called Arnold Guyot that studied these features. And actually, they gave, the people studying these stable seamounts gave the name to this guy because he was really, really nice working on them. And we can define them as a flat top, this is crucial, flat top seamounts, also called table mounts, which constitute rests of ancient volcanic islands that have been eroded down to the sea level before they sank beneath the waves. This is the point. A guyot was an island. When the ocean crust subside, and it's important, for instance, in Hawaiian Central Pacific Ocean floor, guyos rest circa 1,000 meters below the sea level. But when subsidence is not that important or inexistent, which is actually the case of the Northeast Atlantic floor, because of its old age, 180 million years. That means the crust is really old, really cold, really dense, no subsidence is happening. Gallos rest with their summits close to the sea level. That's very, very important. Okay, just have a look to this. Different among drowned islands, gallots, and never emerged seamounts. Here we have a first idea about, this is the way the Hawaiian archipelago emerged. Here the hotspot is feeding the island exactly above the hotspot, in this case the big island of Hawaii. Then when the island is not more being fed, but the crust moves, it became to be eroded, and finally due to subsidence, they drown beneath the sea level, and they form these very nice gallots or table mounds. Here, this is the Great Meteor Seamounts Archipelago, south from Azores, west from the Canaries, and you see the difference between a seamount, like the small meteor seamount, and a gallot, Great Meteor Seamount. And here you can see it even much better. This is the bare gallot in the New England seamount change. This was an island in the past, and this seamount may be or may be not an island in the future, depending on the capacity of accumulating lava. Gallots are not necessarily isolated entities. They may form as well ranges beneath the sea level, like, for example, off Alaska, the Patton Seamount Chain. You see a lot of gallots. They form actually a ridge below the sea level. And here the relation of the interconnectivity among them is much easier than with solitary entities. Okay. Recently, there have been recognized different phases in the ontogeny of the hotspot of Oceanic Islands. Ontogeny is a sort of developmental stages. And six different periods have been recognized. The first one, A, is what we called submarine growth. So here a new seamount is being formed due to the accumulation of lava beneath the sea level from the ocean floor. Sometimes, this is the less likely, those seamounts may reach the sea level and then begin what we call the subaerial construction phase. Then, when the island is not more fed by the hotspots, the erosion destroys them, forming what we call it complex topography with ravines, cliffs, and so on. Erosion goes further on to have basalt islands, finally, the last remnants. And then erosion will vanish the islands above the sea level, and only resting there beneath the sea level you will find this structure pointing to that was an island in the past. So when we saw that, we have the certainty that was an island in the past, and when we saw this, we can consider this can be or can be not an island in the future. So we call that seamounts, and we call that gallots. If you don't have an important subsidence, what is actually the case of the Canaries, we may have a nice family portrait with all the different development stages in the archipelago there. So we have here the babies, seamounts that are now growing, and they may emerge or not in the future. The islands that are really young with subaerial growth, like La Palma and El Hierro, also Tenerife. Islands already that are being down eroded, like Gran Canaria, although with some Pleistocene activity, and La Gomera. Basal areas like basal islands like Fuerteventura and Lanzarote. Here you can see that they are actually a single building. And then we do have here the gallots. Samanay, this is the Selvagians, although belonging to Portugal, they actually are part of the Canarian volcanic province. And finally, here Conception. And have a look to that. I hope you can be able to see. Here we have two sea levels. This is what we call the Holocene sea level. And here is what we call the LGM sea level, last glacial maximal sea level. And the gallots are exactly there, in the middle of both sea levels, here and here. And that's very important for what I'm going to explain to you now. This is La Gomera bathymetry. You see that La Gomera is already in its way to be a gallot. La Gomera was 3 times as large and 2 times as high as it is today. And here is just an array of some seamounts of Iberia and North Africa. And I'm going, it's a pity you can see too much. Well, doesn't matter. This is the North Atlantic Ocean, what we call in an empty view. So no water there. What can we see there? We see a lot of accidents, usually where we do recognize what we see on a normal map. Those are the archipelagos, Azores, Madeira, the Canaries, and the Cape Verde. But you can see that there are much more things down there. Here is an archipelago of seamounts, so-called Saharan seamounts. An archipelago north to the Canaries, we call it Paleo-Canaries. North to Madeira, Paleo-Madeira, so for instance here, the Great Meteor seamounts. But here are more, here, you see even here. So they are everywhere, such structures. If we pick this map, I actually took it from these seamount catalogs. We see how two of them are very close to the Canaries. One is Amanai, north of the coast of Fuerteventura, and another one is Conception, north of to Lanzarote. And here, but there are much many like Dacia. All this is part of the Canarian volcanic province, and here we have these sub-Saharan seamounts that are in the Canarian economical exclusive zone, but do not belong to our volcanic province. They have been formed in a different hotspot event. Okay, here they are actually, the Saharan seamounts. Here you see La Palma and El Hierro, and here they are all of them, like Eco and like Tropic, really big seamounts that were emerged in the past. Okay, some biogeographical implications on gaius of the glacial ages. This is the evolution of the sea level in what we call the last glacial cycle. So from the last interglacial, the Aemean, to the present interglacial, the Holocene, in the last 130,000 years. And you see, it was a funny way of evolving. Here, this is the last glacial maxima, and we are today here, the Holocene. And this is the area, circa 10 million square kilometers in red, that was claimed by the sea after the last glacial maxima. The main areas were Beringia, actually providing a pass from Asia to North America, Siberian Arctic coast, Doggerland in Baltic, we have just think about that, and then here in Asia and Australia, the China Sea, Sundaland, and the Sahul Pleistocene continent. It was not so important in Africa or South America, but here there was a really important shift in area. And what happens actually in Macaronesia? The volcanic set of archipelagos, including Azores, Madeira, the Canaries, and the Cape Verde. Let's have a look. This was LGM Azores. And you see there was what we call an island fusion. So Fayal and Pico grown together, and today this is called Lauri Insula. In Madeira, Desertas and Madeira grown together, but here is really interesting to consider that Porto Santo was 5 times as large as today, just 18,000 years ago. In Cape Verde, it was here another island fusion with San Vicente, Santa Lucia, Branco, Raso, whereas Boa Vista grew 4 times and almost touched Mayo. And in the Canaries, the situation was not that dramatic, but there was a very big eastern reef island called Mahan, and a guyot emerged called Amanai. And I'm going to speak about that a little bit more. So this is the present situation of the North Atlantic. You may recognize it. But this was the situation just 18,000 years ago. 18,000 years ago means the day before yesterday. With a lot of guyots emerging and making a nice step-stone chain from Madeira and the Canaries to Iberia. So just for a short comparison, here we are today. This is now, this was then, Paleo-Canaries 18,000 years ago. The area was doubled, the present area, and the isolation was 2/3 the present isolation. And what is important to consider is that this is the rule, and this is the exception. So we are living the exception, not the rule. And this is not just something of Macaronesia, it happens everywhere in the world. And here we see Galapagos. You see here, Fernandina, Isabela, and Santa Cruz, they have joined in making a very huge island. They are today separate, of course. And have a look to this bathymetry. Again, you see, well, it's a pity. You can't see too much here, but just have a look. El Hierro, and La Palma, and Tenerife, young islands, they have no platform. La Gomera and Gran Canaria, they have a huge platform. They are in their way to being a guyot. We can try to put the evolution of the area of the islands in a diagram, in upsize the time so the last glacial cycle, and in ordinates we have here the area of the islands. And have a look to El Hierro. What happens with El Hierro? Actually nothing. Why? There's no platform, it's too young. No platform happens, nothing with the oscillations. What happened with Gran Canaria? Here we have Gran Canaria. Well, there are nice oscillations. And what happened with Lanzarote and Fuerteventura? Today they are separate islands, they join here. Here, sorry, I haven't said, this is the sea level again, we have already seen it, okay, the sea level. They joined here, this is an island fusion event, again island fusion, and finally, they make a big island, actually 20,000 years ago, only 20,000 years ago, as large as 5,000 square kilometers, and then in the deglaciation, they just lose area and they just became again independent. And let's have, just to finish, let's have a look to the Eastern Canarian Guyot. Again, I have told you already, we are speaking about Amanai, this is Amanai, and here this is Conception. There are more, but we are going to just to speak about them. This is Amanai Guyot. Its summit is today only 25 meters beneath the sea level. I mean, you can even go there with a nice of lungs. You can just take some sand from the summit. It's located 30 kilometers off Jandía Peninsula in Fuerteventura. Whereas Conception, oh, it's not there, Conception. Well, Conception is 55 kilometers diameter and its summit is just 158 meters beneath the sea level. And it's some 70 kilometers north of Alegranza. This is the situation, the present situation of Lanzarote, Fuerteventura, and the islets, and this was the situation in the Paleocanaries. You see here, Amai Seamount. Amai was some 150 square kilometers large and 100 meters tall, and this was Mahan, the union of Lanzarote, Fuerteventura, and the islets, some 5,000 square kilometers large and 950 meters tall. Let's have a look. Here, I try to put again the sea level oscillation in the last glacial cycle from the Aemean to the present time. This is the sea level oscillation. And this is the photic zone limit, which I take some 80 meters beneath the present sea level. Well, we can discuss about that, but I think it's a nice figure to begin with. And here we have this red line is Amanai, today minus 25 meters. And here, this red line is Conception, minus 158 meters. And here we can see how was the evolution of these seamounts in the last glacial maxima, in the last glacial cycle. You see, let's begin with Amanai. Amanai was here submerged. Here emerged Amanai. This blue bar means the island is emerged. And here submerged again. Here emerge again and submerge. And finally here emerge again. This is emerge when it is above the black line, it is emerged. When it is below, it is submerged. And then here we have Amanai that lasts from 80,000 years to 12,000 years before the present as an emerged entity. And finally here it drops again to its present summit, its present depth. So, and what happens with Conception? Conception never emerged. You see it's always clearly below the sea level, but Conception emerged to the photic zone. Emerged to the photic zone, and that means an ecosystem shift from benthic animals to benthic photosynthetic seaweeds or marine phanerogamous community. And actually, island biogeography working. And here we have in green arrows, we do have colonization events, and in red arrow, extirpation, an extirpation in a local extinction, local extinctions. And we see Amanai was colonized by terrestrial land species and animals, and Conception was colonized by photosynthetic species, okay? So this was more or less the situation. And when Conception, in the last glacial maxima, Amanai was 150 square kilometers large and more or less 100 meters tall. Okay, so let's have a look to a schematic diagram. Here we do have Conception Guyot, Amanai Guyot, and Fuerteventura. This is the present situation, the Holocene. You see here we have the high sea level, photic zone, dark zone. Conception is in the dark zone with benthic fauna. Amanai, reaching the photic zone, has a photosynthetic bedding community. And in the last glacial maxima, this was the situation. We have a low sea level, the photic zone and the dark zone, they shift towards the ocean floor. Ammonite emerge, meaning that Ammonite has a coastal crust as Mahan, and Conception Guyot emerged to the photic zone, sharing a photosynthetic bedding community with Ammonite. So this is today, and this was. Okay, and just to finish my dissertation, the Eastern Canaries configuration since the last glacial cycle. Ammonite life cycle during the last glacial cycle includes 3 immersions, 2 submersions in 40 years, 40,000 years, plus stability as island during 60,000 years. Then again submersion, 12,000 years before the present, and finally stability as a Gaia during 10,000 years. Conception emerged from the darkness to the photic zone circa 13,000 years before the present, falling there again 15,000 years later. And Mahan, so the fusion of Lanzarote, Fuerteventura, and the islands, experienced 3 island fusions and 2 fissions in 40,000 years, and then achieved a stagnation of 80,000 years before the present, the last 60,000 years when the sea level was minus 80, for undergoing the last fission just 12,000 years before. Okay, some biogeographical consequences of this story. The emergence of a seamount implies its colonization by terrestrial species from islands nearby by long-distance dispersal, but only the adjustments, shifts in the depths towards the Guyot's bottom of the algae and marine grasses belts to meet the new depth distribution. Conversely, the submergence of a seamount will imply the extirpation or local extinction of the terrestrial coastal species, but only slight adjustments from algae and marine grasses. Dark seamounts emerging to the photic zone have to be colonized by long-distance dispersal from algae and marine grasses, whereas seamounts falling in the dark zone imply the extirpation of algae and marine grasses belts. Both the emergence of new islands or the arrival of dark seamounts to the photic zone will enhance connectivity of the populations inhabiting them. In my last slides, some hypotheses that emerge from this model that may be tested. Ammonite terrestrial biota colonization events stem from Mahan, whereas Conception photosynthetic marine biota came either from Africa, Mahan, or from both of them. Summing up, Pleistocene glacial periods and stadial events within them, the immersion-submersion transition of the macaronesian Gaius may have happened between 50 and 100 times. The reiterative seamounts immersion-submersion transitions should have left behind geomorphological, ecological, or genetic evidences that should be searched for reconstructing their dynamics. And finally, beneath Ammonite summit sediments, pollen or phytolites belonging to the Canarian coastal scrub species should be found. Okay, that was.
Extraordinary presentation. It's just wonderful to have such distinguished scientists here with us this week. I suppose one of the striking features I found from your presentation is in the history of evolution, we play such an insignificant part that our knowledge is there are so many gaps in the context of just the geographical distribution of the physical structures themselves, and not to talk about their ecosystems, which are quite unique. And one of the things, I suppose, if I could open the questions, which I thought was quite striking in your abstract, which is right on the sensitivity of the ecosystems, that it might almost be at a unique point in time in relation to our human interventions or our human impacts, right, in terms of the consequences. I suppose, speaking as a non-scientist, I find that very, very interesting, given the duration of the geological kind of evolution. So please.
Well, I think that actually my idea was a little bit to try to open a little bit your minds in things that maybe in problems that maybe you have never considered, no? But actually some people are working with. I have just asked by a journalist about the impact of the global warming of the human action on this. Oh, I mean, okay. Okay? Yeah, you hear me? Okay. Yeah, well, again, my idea with this presentation was just to try to make you think about something that perhaps you haven't think so far, but actually is a field of research in other fields like island biogeography. And to which extent we can extrapolate these climatic shifts that happen in the glacial ages to what is happening now is hard to say. We are speaking here about ocean sea level shifts of 120, 130 meters, whereas the more pessimistic prognostic of the IPCC speaks about 1 or 2 meters for the end of this century. So I think that are simply not comparable. But what I really consider interesting is to consider that some of the more nice or best preserved submarine ecosystems we do have in the Canaries were actually not that far away terrestrial ecosystems. And this is a very nice transition, how a terrestrial ecosystem shifts to a marine ecosystem in the other way around. I think that's really nice, a nice transition that deserves being studied. And because usually this is away from our approach to the existing ecosystems, no? And I am more speaking about the transitions.
Okay, please, question. My goodness, I started to talk to you, forgive me, please. Yes.
So I'm interested in the bit between the land and the sea, the intertidal, and I'm quite interested in the biogeography of the Northeast Atlantic, both in terms of recent rapid changes, but also trying to understand past phylogeography. The map that you show here suggests that there would be a very, very complex glacial maximum refuge for many, many species in this complex of islands, which presumably as things warmed up, species went to the north onto the mainland, back into the Mediterranean. So all those stepping stones provide a very complex, a much more complex refuge than you currently read about in the biogeographic literature. Could you comment on that?
For sure. Okay, yeah, I can use this. I was not smart enough. Yeah, you are Stephen, absolutely right. There is a new paradigm in island biogeography in the recent years, speaking about the role of islands like macaronesian archipelagos as Pleistocene refugia for continental ecosystems and species. And the old idea that islands where evolutionary dead ends is not more being supported by a lot of new data based in molecular analysis that said that for species shared with the continent, the biggest amount of genetic diversity is actually in the archipelagos, not in the continent. In the continent, there are very few haplotypes when there are more than one, whereas in the archipelagos, Azores, Madeira, the Canes, there are really plenty of haplotypes, pointing to what we call retrocolonization, colloquially boomerang event. And this boomerang event meaning the retrocolonization from island species to the continent seems that have fed actually the North Africa and Europe and the Mediterranean region after the onset of the Holocene, really in an important way. No? So somehow the paradigm is shifting to that idea of island as a refugia, no, of island as dead-end roads, evolutionary roads.
Yes, a little on the same idea. From what you are showing is with sea level variation, you get colonization that vary vertically, but it seems also that regularly, and as you say, last glaciation was yesterday, it seems that regularly speciation is destroyed in a way by regular inflow. So as a matter of fact, yes, islands are not so much as refuge or speciation islands. Is that correct? Is that you regularly speciation is
well, speciation, I mean, there is a how do you say, a schema of the sea level transitions due to the glaciation event that is actually, we are not sure to which amount they are influencing speciation events. Because perhaps these transitions are too short for speciation events. But we do know that, for instance, in Lanzarote and Fuerteventura, they were just a single island 20,000 years ago. We do know that they share a lot of species, more than similar islands in a similar, that have never been fusionated in just single entity. But we also do know that the species belonging to Lanzarote and Fuerteventura have already genetic differences, so they are in the way to evolve to form something new. The problem is very likely the time they will need to make a new species is much longer than the onset of the next glaciation event that will again dilute all these genetic changes. So very likely this is what is happening. No? That's my guess.
Okay, just time for one more question. And
thank you so much for the nice presentation, José María. This question is because I see this process like a bit like a slow process, more or less, not geologically, but in general. What do you think is the role of giant landslides during the formation of the archipelago in this extirpation of species and the evolution? I mean, because while you're seeing the sea level going up and down, meanwhile, landslides are happening and probably they are something there.
Yeah, you're right. But you see, I have tried to differentiate what we call the ontogenetic stages, dynamic of the islands with the influence of the glaciation sea level transitions. Because the ontogenetic stages, there we should put the landslides together with the volcanic activity, together with the island formation, will take much, the temporal scale is much more important. Actually, the landslides are very important to understand the configuration of the present archipelago, for sure, really important. But I think that in the last, as far as I know, in the last glaciation cycle, there was just one landslide in the Canaries, was El Golfo landslide 15,000 years ago. So the landslides, they have a different, say, tempo, and not necessarily the one we are focusing here. On the other hand, I take the opportunity to say that it is not only the sea level what is changing the archipelago configuration. I have just spoken today about that, but we have to consider that also the general marine currents and general wind system have shifted as well, making available new windows of opportunity for colonization. It is said that the polar front has shifted equatorwards all the Hadley cells, so that usually, instead of having the trades blowing in our latitude, we do have had the westerlies, what hence enhance these retrocolonization events. Okay, and on the other hand, also we have to work with the shifts in temperature and precipitation that were really important as well. No? But I just keep my comments to the sea level oscillations.